Hi everyone. Here are some examples of Dalton's law of partial pressure style questions. Dalton's law comes in a bunch of different variations, and these are two of them. If the partial pressures of oxygen, carbon dioxide, and neon in a container are respectively 1.0 atmospheres, 2.0 atmospheres, and 3.0 atmospheres, then what is the total pressure of the system? When I look at my labels here, I have these three pressures for three gases. They're the pressures of the individual gases. This is the first pressure, second pressure, and the third pressure. All I need to do is to find the total pressure is to add them all together. We have this first variation of Dalton's law, which is quite nice. It's that the total pressure is P1 plus P2 plus P3. Now, there might only be two gases in a question. There could be three, like this one. There might even be four, and honestly, there's not going to be four. We're just going to add them all up. It's okay that these are in atmospheres. We just have the first pressure, that's 1.0 atm plus 2.0 plus 3.0. 1 plus 2 plus 3, that's 6. If these were all in kilopascals, that would be okay. We definitely should not ever have a mixture of atmospheres or kilopascals. All we need to do is add the individual pressures up to find the total pressure. Easy peasy. Second example is a little bit more involved. If 2.0 moles of oxygen and 6.0 moles of hydrogen are placed in a 10.0 liter container at 20 degrees Celsius, what is the total pressure? Notice what these two questions have in common. They both ask, what is the total pressure? This one even has the word partial pressures in it. As soon as you see something that's talking about total pressure, it has to be some version of Dalton's law. One of the challenges in the unit is sometimes picking the formula. And Dalton's law does stand apart because of the language that we're going to encounter. What separates the two variations is this one is just about partial pressures and total pressure, whereas in the second example, you can see that there's a volume and a temperature. There's just a lot more different types of information being presented to us. I'm going to put my labels in. 2.0 moles of oxygen. That's a moles. 6.0 moles of hydrogen. That's also a moles. Oh, but we have oxygen and hydrogen. So I'm going to call this one N1. It's our first gas. And then N2 over there for our second mole value that goes with the hydrogen. They're in a 10.0 liter container. That's the volume. And we have the temperature, 20 degrees Celsius. We're being asked, what's the P total? Once I've decided, that it's a slightly more involved type of Dalton's law question, I can put the formula down. P total equals N total RT over V. You might be able to skip some of these steps. I'm going to be really thorough. This equals, so the P total, it's the N1 plus N2. This question only has two gases, so it's just N1 plus N2. There might be three gases in a different type of question. This times RT over V. Now I'm at the version of the formula that I'm going to use. I can start to substitute my values in. N1 is 2.0 moles plus N2, 6.0 moles times R, that's the ideal gas constant, 8.314 kilopascal liters per mole Kelvin. And the temperature is 20 degrees Celsius, which we must convert into Kelvin. 20 plus 273.15 Kelvin. All of this is going to be divided by the volume, our 10 liters. Now we're calculating. 2 plus 6 times 8.314 times 20 plus 273.15 divided by 10. We get 1,949.79928. That's our raw answer. We need to go back and think about the significant digits. Some of the numbers in the question have 2 sig digs. The 10.0 has 3. This means that we want 2 significant digits in our answer. We're up in the thousands. We're going to need to use scientific notation. This becomes 1.9 times 10 to the power of 3. And this was the pressure that we found using the ideal gas law. It's kilopascals. When we're working with Dalton's law of partial pressure, it really does stand out. We're going to see the phrase total pressure in the question. That really helps us identify what's going on. If we have individual pressures, whether they're in atmospheres or kilopascals, we have this, I'm going to call it the nice version of Dalton's law. If, however, we have mention of a volume and a temperature, we're going to have to use the ideal gas law, the expanded ideal gas law version of Dalton's law, where we're going to have to find the total number of moles and then use the rest of the ideal gas law in our traditional way. Pay attention to those significant digits and watch those units, and I hope that helps.